So do we do LNU where U is this, I assume? Okay. So I'm going to call this Y. So this is Y prime. All right. So 1 over U, right? Times. Now I got to use what to find the derivative of this? Quotient rule. Okay. So my quotients. We start with my bottom and square it. Okay. Now the derivative of x plus 1 is 1. Okay. Now when we take the derivative of x minus 2 to the 1/2, we're going to have to use another chain. A different chain. Okay. Let me write that in here just so we can follow. X minus 2 to the 1/2 prime. I already did the prime over here. Are you all getting to the point where you don't write that step unless it's more complex? I hope. Yeah. Okay, good. All right, so x minus 2 to the 1/2, really prime is u to the 1/2, where u is x minus 2, right? Yeah. So 1/2, u to the negative 1/2 times 1. All right, so that is going to replace this right here. I'm just going to do it right now instead of rewriting the whole mess. So 1/2 x minus 2 to the negative 1/2. I'm already putting u back in. Didn't give myself enough room. Time, that's it, right? Okay. All right. Now, remember, when you take 1 over u, and u is a fraction, what can we do with 1 over u? Just flip it. So let's do that right now. 1 over x plus 1, blah, 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 is x minus 2 to the 1/2 over x plus 1. That takes care of that complexness. Okay. All right. What's the bottom x minus 2 to the 1/2 squared? X minus 2. Okay. This is x minus 2 to the 1/2 minus, now we have a complex fraction here. I'm going to put x plus 1 over 2 and x minus 2 to the 1/2. Okay? Did I lose anybody? I know it's complex, so you got to figure out what you're going to do with it. Do what? I just have to calculate how it goes. Okay. No, not with this thing sitting there. Okay. All right. However, if we distributed, that would take care of that complex piece except for the 2, right? Let's do that then. Did anybody try that? Okay. If you distribute this, it'll be nice. You distribute this, that will cancel, so it'll be nice too. So we're going to distribute. I don't know why I'm writing it, but here we go. Okay. This times this. Okay. So on the bottom, I'm going to have x plus 1 and x minus 2 when I distribute. So far, so good? All right. X minus 2 to the 1/2 times x minus 2 to the 1/2 is x minus 2 minus x minus 2 to the 1/2 times x plus 1 over 2. Okay. So that's not going to be too bad. That is not, by the way, what I did originally. I just thought when I redo it now. I'm going to get rid of that 2. Okay. So I got 2, x plus 1 and x minus 2. On bottom. I have 2x minus 4. I got to multiply that 2 by the whole denominator. And what do I have after that? X minus 1, right? I probably wouldn't at this point. I just leave it as one fraction and just combine like terms. So I got x minus 5 over 2, x plus 1, x minus 2.
one fraction is usually better than two. Because if we were to solve that equals 0, we set the bottom, top equals 0. If we were looking for a, vertical tangent, we set the bottom equals 0, so we'd be all ready to go. Did anybody get that first time around? I didn't even get that first time around because I went a different route.
I can't read X minus 1.
Well, yeah, but just, so if you didn't distribute and you I separated and then it just got weird and ugly, right? The problem with going a different direction is not a problem unless it's a multiple choice question and you're like, okay, I got that and that's not one of my choices, but that is. So it would be hard to, do that. So that's why you have to simplify. If we went the other way and you got some weird answer, even if it was right, it's probably okay for free response. Yes.
So the only way that you can do like a negative outside the bottom and everything on the bottom is being multiplied.
Yes, exactly. So if like you have x, y to the minus 2 over z, y, you could move that y squared down here.
Okay.
Yes, but it has to be all multiplication. Good question. Okay. All right, let's try. There's my F. Hello. There we go. Interesting. Have one on 11H, maybe? Oh, yes. Okay, this is a whole different thing. All right. Logarithmic differentiation. It's really weird and ugly, but it is necessary sometimes. I need to get this down too. Yeah. So that's why we need the log rules for this more than anything else. So I haven't found the juniors kind to be whining now that our one junior is gone. Are they with you?
Oh,
The juniors. I have not found the juniors this year to be whiny. In the past they have been. Not you all, but no, they weren't like
like they come like on today's day they come straight from the
they're a little uptight, probably. They're very sweet.
You also have so many of them.
Yes, I do have a ton.
DC people.
There's a lot of them in there.
Like we how their own class was.
Yeah, there's
I guess it's small.
25. I usually have, yeah, it was 11 last year.
Do all these drop?
What do you mean drop?
Start it and then not finish it?
That's very unusual.
Well, she jumped from advanced.
Yeah, she jumped in advanced safety.
Yeah.
Okay, so we're going to take the natural logs. Oh, true, I forgot about that. I mean, I wasn't saying she's whiny, I'm just saying you can, because they are not whiny classes when I
Oh, well, they come to chemistry.
Okay.
Which I guess
They're just a little stressed out, or they actually. Exactly. Okay. So we're going to take the natural logs of both sides, differentiate implicitly. Some of y'all missed that on the problem today, and then solve for y prime. Because that's what you have to do when you have implicit differentiation. All right. When do we use logarithmic differentiation? We have two instances, really. What, honey? Yes, yes. And that's what y prime is. Slash d by dx. Or you would say d by dx, right?
think.
Okay. You like it. All right. When to use logarithmic differentiation? When both variable and exponents are, base and exponents are variables, like that. Okay. And the other instance is when we have a unreasonable amount of powers. Unreasonable power. Which is, okay. I think the next example. Now, in the book directions, please pay attention to the directions. I don't know which ones, but one section specifically says use logarithmic differentiation. So be sure you do that, otherwise it's going to be a mess. Okay, so square root x to the square root of x. All right, take the natural log of both sides. Here we go. ln y equals ln x radical x power. Okay? Now, what?
She's on Winter.
Lee was sitting right here. All right, I'll post the rest of this. Okay, so what do we want to do here now? We're supposed to use logarithmic rules to simplify. Move that exponent to the front. And remember, when it's moved to the front, it's multiplied. It's a factor. Don't forget that. I'm going to put the dot in there so we can find ourselves things. Okay? All right. Now, we're supposed to differentiate. Okay? We can't solve for y, so that's why it's implicit. So now we're going to differentiate both sides. Okay. What's the derivative of ln of y? 1 over y, what's the rest of it? dy dx. Okay? dy dx doesn't have to go with the y, it just has to be multiplied by. Okay, what are we going to do for that? All right, Prime's rule. This is x to the 1/2 ln x. All right. Derivative of x to the 1/2 is good. ln x plus x to the 1/2 left alone. What's the derivative of 1 over x? Oh, whoops. 1 over x is the derivative of ln x. Okay. Again, are you all getting to the point where you don't have to write that prime piece out at all? Yes, good. All right. Here we go. We only have one dy dx, so that's nice. So dy dx, getting it by itself is going to be just a matter of doing what? Multiply by y. And we'll clean up while we have it. What's this together? X to what power?
X to the 0. X to the
X to the -1. Right?
Negative 1/2. Wow. That was a struggle. All right. Now we're officially done, but remember, y is a simple little thing. Let's just put it back in. And then we have our differentiation in terms of y. How do you know when to do that? So I just plugged in my y, my original y. Okay? If you have your original function solved for y, your derivative should be in terms of x, not in terms of x and y like normal implicit usually is. Does that make sense? So that's when you should substitute that y in. You could leave it like that. You could have it factored if you want, but you could. I would not, because this distributed here is not going to combine nicely with the negative 1/2 and the radical x, so just leave it alone. It's factored, it's good. Okay? That's my answer.
Oh, no, just kidding. I didn't see that one.
Okay? You could pull out x to the negative 1/2 out of this other piece if you like.
Yeah, extra.
I mean, it's not really any better. It's still a fact. Okay. Oops. Dang it. All right. Let me kind of go into about that other moving power.
Unreasonable amount of power. What does that mean?
Like, they're crazy now. Yeah.
Well, I was thinking you meant a bunch of verbs. I was like,
No. So on 3-7, let me just highlight here the ones that are requiring logarithmic differentiation are 33 and 36 and 38. The last three. All right, so let me take one of those from the book. How about, no. How about 33? We do 33. How about 34? Because you're doing 33, right? Yeah. All right, 34. 27, yeah. All right, 34 looks like this. Okay? 33 was, when you get that, this is the unreasonable, you get y equals something to the 5th, and you get something else to the 6th. Okay? So it's easier, it's not a horrible differentiation, 33 is not going to be if you use logarithmic. Okay, but if you didn't, it would be because you have to use a product rule, and of course you rule each of those factors. Okay. Alright, so logarithmic differentiation, I don't know if we're going to finish, but we will do our best. Okay. We got a bunch of, what's the first thing we do with logarithmic differentiation? ln both sides. ln y, ln. Okay? Now, can you already see why this would be easier? Because instead of doing all the multiplication, we're going to do what? What does this? There you go. Okay, so you're going to do addition, because we are multiplying those numbers, right? This is x to the 1/2. So now with the exponents, we're going to pull those around front as factors. I'm going to put the dot there just to remind you that's a multiplication. X squared times, do what? Times ln e, and 10 times ln x squared plus 1. Okay? Still equal to ln y. Remember. Okay. Now what? Okay. All right, and remember we're differentiating. We haven't started that yet. So we take the derivative of both sides. Okay. We're so involved in our logs we forgot what we're doing for a minute, which is easy to do. Okay. What's the derivative of ln y again? See what you get. Okay. All right. 1/2. It's a constant multiple. What's the derivative of ln x? 1 over x. Okay. What's the derivative of x squared? 10 is a constant multiple. We're going to have to use the u. ln of u, where u is x squared plus 1, 1 over u, x squared plus 2x. Say it again, Sarah. Or did Sarah not say that too? Oh, gosh. Your voice is... Okay. All right. Well, we must be sounding the same. All right. Must.
Good morning, teachers and students.
We're going
We come to you at the end of our D block classes today. We are going to prepare to gather for our All Saints Day liturgy celebration here in just a couple of minutes. Teachers, we do need to get started right at 10 o'clock today, so we need your help and cooperation with moving quickly to the gym. Listening carefully for instructions from both the teachers and the ambassadors about where to sit. And then again, moving quickly, as we do need to start at 10 a.m. this morning. Couple of reminders. One, Mrs. Studerman has been sending us reminders about the importance of participation in our liturgies, and how our participation together helps us to make a more powerful and meaningful experience for all of us. So we appreciate your attention to that, and thinking about a way that maybe you could more fully participate today. So engage with engage